So in this first part of the experiment, your job is to torture a dolly. So for the first question, you put the doll on the back of the cart, and then we're going to yank the cart forward and describe what happens to the doll. Like that. In this first question, it's probably most useful to talk about how the doll moved relative to the table. In the second question, we don't want the dolly to fall off the cart in this case, but we are going to smash him into a brick wall as hard as we can. So you may want to pull a little gently at the beginning so he doesn't fall off, and then smash him into the wall. In this case, it's probably more useful to talk about how the doll moved relative to the cart rather than the table. The third case is exactly like the second, except this time we're going to give Dolly a bit of a seat belt. So you put the elastic band on so that he's now got a seat belt, and then again we're going to smash him into the brick wall. And again, we describe how the doll moved relative to the cart. Question 4 is where you're going to explain the physics of these three cases. They specifically tell you to think about inertia, which is the idea of resistance to change, but it's also incredibly useful when you're trying to describe these three cases to think about Newton's first law, which is that a body at rest tends to stay at rest, and a body in motion tends to stay in motion unless it's acted on by a force. That one law describes these three cases. You just need to think about how. In this part of the experiment, we have a cart on a track, and it's got some added masses on it, and we're going to apply forces to this cart and then measure the acceleration of it. So we'll be using that acceleration program, and I'll give you a short refresher on how to use it on screen in a moment. As always, the first thing you want to do, however, is level your track. Find the bubble that's going horizontal across the track, grab the screws on the bottom of these legs, twist them in the same direction at the same time. Put it upright like this, then you'd want to go to one end of the track and grab the screws on the bottoms of two of the legs and twist them at the same time in the same direction. The way in which we're going to apply forces to this cart is with this mass hanger. So it's attached to a string, and you can hang it over the pulley at the end of the track and then hook it onto your cart here. And that then accelerates your cart down the length of the track, because the string is giving you a horizontal force on the cart in this direction. So you're going to capture that motion on screen, fit a straight line to your velocity time graph, and that gives you the acceleration of your cart. Now we're going to study 4 different cases in this experiment, and we're going to compare the second case to the first case, the third case back to the first case, and the fourth case to the first case. So that first case, this one here, is going to be our control, and the other 3 cases get compared to it. That means that the graph we're going to make for this first motion is actually going to need to be pasted in 3 different locations in your report. I'll show you where later. And again, the first motion that you're going to study is going to be just the cart on the track with all its added masses, and you would start your program running and then release this and let it accelerate down the length of the track. And that's your first trial. For the second trial, what you'll do is you're going to take all of the masses off of here, flip the cart upside down, and then put the masses back on. And you're going to make a graph of this also. It's not going to be a very interesting graph, obviously, but you'll make one and you'll figure out what the acceleration of this is. And the point of doing this trial is that we're still applying that horizontal force to accelerate the cart down the track, but the cart's not moving anymore. And why is that? Well, because there's another force involved here. So this horizontal force is no longer an unbalanced force. Now there's 2 more trials that we'll do, but before we get to them, you first need to do question 6 in your lab manual. So I'm going to give you that quick refresher on how to use the acceleration program first, and then I'll give you some tips on how to do question 6, and then I'm going to come back and show you the next 2 trials that you do on the track. So as usual, you open the Physics 1100 folder, and you're going to want this acceleration program again. So open that up. And in your first trial, the cart's right side up with all its masses stacked on it. The mass hanger is attached to it via a string going over the pulley. So to do your experiment, you pull the cart back, and then you'll click Collect and release your cart. And if you need to, you can adjust the size of your graphs the usual way. You click the highest number and type in something that you think will work. And that also works for the lowest numbers. So now I can see the linear part of my graph, and I'll adjust this one as well. And the cart was being uniformly accelerated, so my position time graph looks like a curved line as expected, and my velocity time graph basically looks like a straight line as expected. So I would highlight the linear part on my velocity time graph, and then to fit a straight line to it, I would either go Analyze, Linear Fit, or I can click this Linear Fit icon at the top. So I'll do that. You can move your box around if you need to, and this box of information gives me the slope of the graph, which is my acceleration. Now the manual tells you that you're supposed to print out both of these graphs, but I will let you know that the velocity time graph is actually the only one that's worth marks. So screen capture your velocity time graph the usual way, and I'll remind you again that you're going to be pasting this graph into 3 different locations in your report. Another thing I'll mention here is that the manual tells you to report the acceleration of your cart for each of the 4 cases we're studying. That means you need to write the acceleration down. So you paste in your graph, but you also need to write in your acceleration into your lab report. That is worth marks, and it's easy to forget to do. So now I'm going to show you the next trial's graph also. So for the second trial, remember that you took your cart, flipped it upside down, and put the masses back on it. Then you would click Collect, and just make a graph of this motion also. Highlight a section of your graph that looks pretty linear, fit a straight line to it, and then this goes in your report also. So once you've gotten your first 2 graphs, then you can move on to question 6 in the lab manual. So now I'm going to talk about question 6, but I'm zoomed out for a reason, and that's because I want to talk a little bit about question 5 again. So scrolling up to question 5, recall that this is the case where you had the cart right side up and it accelerated down the track due to the mass hanger. And I mentioned that you need 3 copies of this graph in your lab report. So where do those 3 copies go? Well, the first one goes right here for question 5A, and then you'll have 2 more copies that need to go in your book. So where do they go? Well, the second one goes here in question 7A, and the third one goes here in question 8A. So in all 3 of those cases, you've always got a second graph, and you're going to compare the 2 graphs to each other. But that first graph that you made goes in questions 5, 7, and 8. So now let's go back and talk about question 6. So in question 6, there's several little questions you need to answer in it. And the first one is, when a force acts on an object, what happens? And your answer should be some variation on, well, it accelerates. However, that's not the full answer, but I'll leave it up to you and your partners to discuss this and come up with a more complete wording. The next thing they ask you to do is to expand on that answer that you just gave by talking about 3 other cases that you've already looked at. And those 3 other cases are question 3, which was the doll with the seatbelt, question 5A, which is when the cart was right side up and the mass hanger was accelerating it down the track, and question 5B, which was the cart on the track but flipped upside down. So the mass hanger was pulling on it, but it wasn't moving. And again, in this question, we're talking about forces acting on objects and whether or not that causes acceleration. And you're going to discuss these 3 cases. So doll with the seatbelt, cart accelerating down the track, and upside down cart not accelerating down the track. And talk about how the forces are either causing acceleration or not causing acceleration in those 3 cases, and how that explains the motion you saw. So now I'm going to show you how to do the third trial. It's basically just like the first trial, except with one change, and that is, we're going to take our mass hanger, and we're going to take 50 grams off of the cart and put it on the mass hanger instead. That basically doubles the mass of the mass hanger. Then it goes back over the pulley, and the reason why we did this is that we kept the mass of the whole system, everything that's being accelerated, the same. So cart plus mass hanger, the mass of all of that stays the same, but we've effectively doubled the force that's accelerating the cart this way. So same mass, double the force, and we're going to study how that affects the acceleration of the system. So you would start your program running and then capture the motion of this accelerating down the track. In the fourth case, we're going to take that 50 grams back off of the mass hanger, and we're going to put it on our cart again, but we're going to take the other masses off. So just 50 grams goes here, and then the bare mass hanger is going back over the pulley. And the reason why we're doing this is we've effectively halved the mass of the whole system, but the force that's accelerating the cart down the track is the same as it was in case 1. So half the mass, same force, and we're going to study how that affects the acceleration as well. So you'd start your program and capture a graph of this motion. So now I'm going to give you some hints on how you do questions 9 and 10, which relate specifically to these last two trials. So in question 9, it's all about those two cases you just studied on the track. So question 9a says, if we double the force on a system, but keep the mass the same, what happens to the acceleration? So you would go back to question 7 and write down your actual values for the accelerations here, so real numbers. And you want to look for an obvious proportionality. So did the acceleration get twice as big, half as big, 4 times as big? Look for obvious proportionalities and answer this question based on your actual numbers. In question 9b, they ask, if you half the mass but keep the force the same, what happens to the acceleration then? So again, you'd go back to question 8 and you'd write down your acceleration values here. And then you'd try to identify obvious proportionalities and say what happens to the acceleration when you half the mass but keep the force the same. And then question 10 is where you bring it all together and you say, how does the acceleration depend on force and mass? So you're going to write down an equation here, and hint, hint, it should look suspiciously similar to something you've seen in class, but you bring it all together based on your data. So you write down that law, and then you need to explain how this law that you just wrote down helps you explain all the results you've gotten so far. Specifically, you want to talk about the 3 cases with the doll and the 4 cases with the track. So you go through each of those and you talk about how this law that you wrote down explains what you saw in all of those cases. And to get full marks, you do need to talk about all 3 cases of the doll and all 4 cases of the track. In this part of the experiment, you have 2 carts, and they've both got force probes. So one of them's got a loop on it and the other's just got a post. And you're going to bounce them off each other like this, and measure the forces they exert on each other with these wireless sensors. So here is a slightly fuzzy close-up of the 2 sensors. First thing you want to do is turn them on. The little red light will start flashing, and when you get them connected to the program, that red light will turn green. Another thing to take note of is these little ID numbers here. So these will help you identify your 2 sensors out of all the sensors that are in the room. You will need those to set up the program. I'll show you the program you're going to use to do that in a moment. So one thing we're going to do, however, is we're going to put a mass on one of the carts, and we're going to call that the truck. So the truck is heavier. So this is a car, and this is a truck, and the experiment is to collide them into each other in different ways. So sometimes you'll collide the car into the truck, or the truck into the car, or you'll collide them together, like that. And then you're going to watch the forces that they exert on each other on screen and draw some conclusions. For the car and truck part of the experiment, as usual, open up the 1100 folder, and you want to open this Lab 5 program. Now I'm going to resize things a little bit so that you can see the equipment at the same time. And like before, the first thing you want to do is to connect your 2 wireless sensors to the program. So start by turning your 2 sensors on. The light should be flashing. And then to connect them to the program, click this little icon here in the corner, and it's going to hunt around for all of the wireless sensors in the room. Now that means that it might pick up everybody's sensors in the whole room on every desk, so that's why it's important to check the ID numbers on your 2 sensors, and then connect only to those 2. So you'd connect both of them, and once it's found them, you can click Done. And now the program is able to read information off of our 2 sensors. There's one more thing you should do before you start taking data, and that is you should zero both of the sensors. So go down here to these 2 buttons, click each of them, and then click 0 while the sensor bumpers are not touching anything. So do that for both of them. And now you are ready to take some data. So what you do is you click Collect, and then you can bounce these 2 vehicles off each other. And you can see that in real time on your screen. So you would follow through the lab manual and study all the different situations it tells you to study, and you'll capture the graphs that you need and paste them into your report. And obviously what we're studying here is Newton's 3rd law. When a body exerts a force on another body, it experiences an equal and opposite reaction force on it. So you're checking whether that's true based on your graphs. Do the forces look equal and opposite even though the truck is much heavier than the car is? Now on the last page, question 12, I'm going to give you some very minor hints on how to do this. So there's 3 questions, and in each of these cases there's a little diagram and an arrow showing what direction the force that's being exerted is pointing. So for example, a person kicks the ball or the person pushes on the floor. In each of these cases, you'll name the reaction force, and you also want to draw in the vector for the reaction force. So you draw an arrow on the diagram showing what direction the reaction force points. When you're naming the reaction forces, I don't need you to tell me the official name for it. You can just describe it in words to me. So for example, the person pushes on the ball. What does the ball do back to the person? You could describe it in words. The person pushes on the floor. What does the floor do back to the person? Again, you can just describe it in words, or if you know what it's called, go ahead and give me the official name for that reaction force. I will warn you that the third case, down here at the bottom, is fairly tricky, so I'm going to give you just a very modest hint in the way I'm wording things. In this case, the Earth is pulling on the person gravitationally. What does the person do back to the Earth? So think about that carefully with your partners. That's the only hint I'll give you.